Well, thanks a lot. So it's a pleasure to be here on this Taylor lecture. And the idea of today's talk is trying to tell you about the work that we are doing on layer materials and some of the latest things that have happened here at Penn State and elsewhere. So here we have these triangular shapes that are, well, this is like photoluminescence coming from tungsten disulfide single layer island that I will talk about. And the point here is really trying to build new materials just layer by layer. And then we will get a three-dimensional solid that is basically has unprecedented properties. So this is something I will talk about. And of course now, let me tell you how things, so about the importance of interdisciplinary research, and this is something that it's been stressed here in the Taylor lecture, and it's necessary to solve very complex problems. And I think that's the philosophy of Penn State, and that's what attracted me to come here to Penn State. And so why is this important, multidisciplinary research? Because nature is not organized the same way as universities are. So usually at universities, we want to have different departments, and interactions between departments sometimes or between colleagues is not very common, and we want to strengthen that. So this is the way, a new approach to really solve very complex problems. And of course, international collaborations are very important, and we'll show you some of the things. But regarding this multidisciplinary approach to solve very complex problems, then we have here created a new center here at Penn State. Was approved by the Vice President of Research. So it's a research center which is multidisciplinary, and the College of Science, the College of Engineering, and the College of Earth and Mineral Sciences are together, working together with the Materials Research Institute. And we have a critical mass of colleagues with different expertises, and if we join them together, then I'm sure we'll get lots of exciting things and results. So these are the 13 faculty members from different departments, from physics, material science and engineering, electrical engineering, chemistry. And the point here is to solve problems related to two-dimensional systems. And of course, one of them would be graphene, but there are other materials that I will discuss during my talk. And so this is just a new adventures here with this new center. And so this is sort of, it was seeded by a MERS Exceed project. So we together with Vin Crespi, we were leading a MERS Exceed project on two-dimensional materials, and this sort of came up that we have the critical mass to start solving very complex problems. So this is myself, and so let me show you some of the work that I will discuss about. So these are people from the group. So we have graduate students, undergraduate students, research associates, postdocs. We have visiting scientists. So it's a very truly international team and truly multidisciplinary because we have students from different departments. I think that's very rich, very nice. So of course, international collaborations, as I showed, is multidisciplinary effort as well, and these are collaborations over the last 12, 10 years that we have had. And of course, some of the work that here is being funded by the MURI as well. MURI on 2D layer materials that started 2 years ago. And we have all our Penn State collaborators, which are part of the center, of course. Eric Hudson, Nathan, Jun Shu, Simon Liu. Okay, so this is a picture that we took last week, so it was still nice and warm. Now it's a bit colder, but this is the team members. These are the team members. So basically, these are the people that are doing the work, and there are some of them are in the audience. So let me talk about layer materials. This is something that Richard Feynman said in his very famous talk about. He was really trying to say we can really arrange the atoms the way we want. What would happen? Is it really possible to locate the atoms in the positions we want and just to look at the properties? And this is basically a famous phrase that when we have some control of the arrangement of things on a small scale, of course we will get lots of new exciting things that we can see in substances. But he also said something before this phrase, and he said, what could we do with layer structures with just the right layers? And this is something that and now it's coming into play because if we have different layer materials and we stack them one on top of each other, I think we'll have a new van der Waals solid with unprecedented properties. And so this is the way I will, I will discuss about this control of how to make a material just atom by atom and layer by layer. So let me just introduce you some of the layer materials that you may know. And these are, for instance, graphite. Of course, you have this on the pencil leads. I mean, Josh Robinson have talked about graphene, just one single layer. We have boron nitride. This is an insulator. This is semi-metal. You can have the hybrid between the two. This is boron carbon nitride. So this is a semiconductor, depending on how the boron, the carbon, and the nitrogen atoms are arranged. You have also carbon nitrides, which could be layered, and these are hypothetical structures. But you have also chalcogenides, and you have other layer materials, but chalcogenides are a bit more complicated. I will also talk about that. So you have a metal atom here, and it's sandwiched by sulfur or selenium atoms. So the point here is that it's like, typically it's like a three-layer. So it's a tri-layer system, but they have van der Waals interactions, and then you create a solid out of this. So the point was with layered structure. So if you take a single layer and you start to bend it or curling it, then you can get zero-dimensional nanostructures or one-dimensional nanostructures. And this happened with carbon. So let me show you. So with carbon, you can get from a graphene, so you can vaporize graphene, and then you end up having fullerenes, which could have this behave like the superatoms. So you have these crystalline structures where the fullerenes are like the superatoms, and you can roll it also into tubes, and you can make tubes. So you can make carbon nanotubes, you can make fullerenes, but you can also use the other layer materials like molybdenum disulfide. You can make cages as well, or you can make nanotubes of these materials, or you can make also boron nitride tubes or cages. So the point is, with any layer material, you can curl it. If you know how to curl or how to bend it, you have to introduce defects, and then you can make new structures. And this was the topic of research for several years after the discovery of fullerenes in 1985. So let me just show you, this is just one example, just carbon, but this could happen with any layer material, it's not only carbon. So with carbon you can get you can get 0, 1D, 2D, 3D. So all these structures, so you have 0-dimensional, 1-dimensional, 2D, and 3D. So this could happen with any other layer material. So with carbon it has been amazing because in a very short time you get 2 Nobel Prizes, one in chemistry, one in physics, one 0D, this is 2D, and then you have 2 Kavli prizes related to carbon nanotubes. Of course, there are many things that could happen here in the 3-dimensional stackings and try to make hybrid structures, which we're working on. But this is just one example with one single material. So the point is this could be extrapolated to other materials, and we can learn lots of things about other layer structures. So there's plenty of room in the layered world, and this is the point of my talk. So just to show you the amount of publications, just the carbon, I mean, I will not talk much about carbon, but just to show you that when you have 17,000 papers published every year, it's impossible you can read those. So you can see it's a it's increasing. Graphene is also increasing, so 7,000 papers, 2011. So you can see how the field is moving. But let me talk about something about carbon. So I will just talk one system, and this is doped graphene. I think Josh gave a very nice introduction about graphene, architecture graphene. So this is CVD-grown graphene. So this is not Walter de Geer's favorite, but it works for us. So the point is, as Feynman stated, can we place the atoms in the positions we want? And when you come to graphene, so can you place the atoms in the different sublattices? Can you control the placement of the atoms? And the answer is yes. We know it happens, we still don't know why, but it could happen. So I will show you. And related to these topics of doped graphene, so the number of publications is increasing. You have last year was about 900 publications. So this is also moving forward. So I think Nitin and Josh, they talked about this. Doping of graphene, you have this drag cone. When you have N-type doping, you just shift the Fermi level. You have the P-type doping, you have the Fermi level shift in the other direction. So one of the ways to play around with this is just by substitutional doping. So we'll introduce nitrogen. And there are many papers that have appeared recently related to the synthesis and some applications of these nitrogen-doped graphene. So like high-frequency FETs, biosensing, metal fuel cell catalysis, ultracapacitors, photovoltaic devices. So all of them, they made the graphene, the nitrogen-doped graphene with using different techniques. But none of them really tell you how the nitrogen atoms are embedded in the graphene lattice. Because there are different ways the nitrogen could be bonded to carbon atoms. And then you get different properties, different reactivities, different electronics. So this is what we're working on. So let me just show you, this is some of the work that we did here. Here at Penn State with Ritau and, of course, members of the group. So the idea is just to use atmospheric pressure CVD systems in which you start growing graphene by passing methane. So methane, then you grow this on a copper foil. It's not a silicon carbide. And then you reduce the temperature a little bit, and then you inject ammonia. And that's the way to dope it. That's the best way to dope it using our conditions. And then you use your graphene. You don't see it. That's a copper foil. But you can extract it. So you can etch the copper foil, and you can just place it anywhere, and you can transfer it to other substrates. And what you see here is where you have your nitrogen-doped graphene, or it could be your graphene itself. So when you come to the TM, and then you see, well, you see this single sheet. This is a two-dimensional system, which basically consists of carbon atoms, and there should be some nitrogens there, but here you have a monolayer. 90% of the material we made is it's monolayer. Then we have bilayers and trilayers, which also is a byproduct of the synthesis. And of course, this could be tuned even further if you want. So one of the things that also Josh mentioned is about Raman spectroscopy, and I will not get into details, but by using Raman, you can basically identify graphene, and this 2D band is very intense in graphene systems. So this is the G band, and this is the D, which is not very much, which is related to defects. So when you put the nitrogen-doped system into the Raman spectrometer, you start to see D band increase and the D prime band, which is sort of characteristics of this nitrogen-doped graphene. So we have done some mappings of the materials that we make, and of course in these areas we know this when you do the ratio of the intensities of 2D over IG, then you get this is signal of one monolayer, and you keep these dark spots are signals of few layers. And you do AFM, you go back, and this is just you can basically confirm that these are related to multi-layer growth. So the best way to know about the binding energy is just by doing XPS. So it's a surface characterization technique. And here we just noted that with our conditions, we have one binding energy. So that means that nitrogen was bonded to carbon in one way. So this is around 401 electron volts, which is related to this 401 is nitrogen bonded to 3 carbon atoms. So here, by looking at this peak, we know that nitrogen is bonded to 3 carbon atoms within the lattice. And the important thing is how we want to identify where the nitrogen atoms are, and then you have to use STM techniques. And this by STM, you can see clearly across the hexagonal lattice, and you can see also some brighter spots which are related to the nitrogen. Of course, nitrogen has 1 electron more compared to carbon, and you start to see some features here. So you can see these features are related. We found them very often within the surface here, and this is an enlargement of them. And the explanation is that you have 2 nitrogen, so it's a double substitution. So you have very bright spots, which are the carbons here next to the nitrogen, but you have 2 nitrogen atoms there. You have also the density of states, experimental density of states. You are injecting electrons in your conduction band. You have these states here. But important thing is that these nitrogen atoms go to the same sublattice. So it's very interesting because they don't go to different sublattices. They go to the same sublattice. So in graphene, you have 2 sublattices, A and B, and I will discuss about that. So basically, these orientations of the triangles means that the nitrogen atoms are in the same sublattice all over the sample that we check, or most in the majority of the sample. So we have a preferential. The nitrogens like to go to the same sublattice, but everywhere in the sample, and this is the type of defect we have. So by looking at a paper by the Columbia group, they also found with single substitution. So we found a double substitution. This is they managed to dope graphene with single substitution nitrogen. And they also have this orientation of the triangles in the same sublattice. But again, they didn't talk about much about that, but then we noticed, oh, this is something interesting. So you have sublattice A and B, and the idea is that if you put your nitrogen atoms in a balanced way in sublattice A and B, basically you just shift the Fermi level, and there's no band gap opening. But when you start to imbalance the doping, and you start to put more nitrogen atoms on sublattice A rather than sublattice B, you start to open a small band gap. And there are some good calculations by Jean-Christophe Charlier that he has demonstrated recently, theoretically, that if you put you can put up to 8% nitrogen, if they go to the same sublattice, basically you can have a very wide, very, very large gap, like 600 milli-electron volts. So this experiment, this is theoretical when we're trying to do the experiments, but you can have a decent, if you have 1% or 2%, so it's something in between. So it's few milli-electron volts. Okay, so we have found other types of defects. I will not discuss them, but these are very rare. The defect that we are concentrating on is this one that goes to the same sublattice, this is the energetics of this defect. And then we have the experimental simulation STM and STS, and this is the simulated one on P where the two, between the two nitrogens, it's very similar to experimental and theory. So, as I showed, so can we really arrange the way, these nitrogens go to the lattice? And the answer is yes. So if you fine-tune the conditions, so of course you can see these big changes in the Raman spectroscopy here, and you can change different temperatures, you can have different times. And for instance, you have this case, and this is some work by Ximing Feng. So basically, you get no nitrogen doping here. But if you do it at lower temperature for a longer time, you have here, this is very interesting, you have the double substitution, which is here. But you also have these arrows, which is the single substitution. So it's possible to tune the single and double substitution, and we can have one more or the other. And I think this is very, very interesting and important. And of course, that is to tune the electronic properties. Some of the applications of these substrates is that when you put a molecule here, for instance, rhodamine B, when you put a molecule there and then you shine your laser, but basically there is no signal, you cannot identify for some molecules like are used as markers. But if you use your nitrogen doped graphene as a substrate, you have this Raman enhanced signal, and you can see these stars, the peaks are related to this rhodamine B when you use the nitrogen doped graphene. When you use pristine graphene, it doesn't work very well. And you have crystal violet as well that works in a similar way. So these are some of the applications of this nitrogen doped graphene. And of course, you could dope with boron, which is just next to carbon in the periodic table. And this is some work that Ritau and Ember and other people in the group Anu are doing. And this is a bit more complex. When you try to put boron, then you get this croissant-like molecule. Croissant-like feature, this is the experimental, this is theory, and we're finding new things, new physics there and at low temperatures, and I hope next time I can show you the results that we have. Okay, so that was with graphene, with carbon. So, but that's not the whole story of layer materials. And so the important thing of layer materials is that you can start playing with insulators, semiconductors, or even metals and superconductors. And the point here would be, what happens when you start to decrease the number of layers to the properties of the material when you have just one single layer? And you can have these alkyl toluenides, and you can have other layers. So I think there are books of layer materials, there are plenty of layer materials that you can play around. And I think the important thing is if we understand layer by layer what's going on, I think we'll get new physics and new chemistry behind. So I will just show you about nitrogen, boron nitride. I think I will go very quickly with this one. But the point here, this is an insulator. And what we did is we transformed this boron nitride mesoporous carbon into this mesoporous carbon into boron nitride just by having this reaction at high temperature in nitrogen atmospheres. So this is some work that I did myself when I was in Japan in 2004, and we published this paper in 2008. But I think that was very interesting. The material that we had, it was basically consisted of just boron nitride, so you can see there's only boron and nitrogen. But you have lots of edges, and this, we call these spiky balls. And when you see the high resolution, you see these edges, you have these exposed edges everywhere. And that was interesting. So we decided to do field emission, electron field emission measurements of these balls, of these arrangements of balls. And then the interesting thing we found is that these things emit like a metal, so, but boron nitride is an insulator. So we checked several times, and it was always the same. So we were getting like around 1.2, 1.3 volts per micron, which was like a metal, so very low turn-on voltages, and we have the electron emission. This is the current stability, which is, well, it changes a little bit, but it takes some time to get stabilized, and it's sort of there. So one of the explanations we had at that time is that when you have boron nitride, you have edges here. When you have zigzag edges, so you have this, the band gap here, and when you start having edges, you start to introduce, this is the edges from the, this is the bands from the edges that you start crossing the Fermi level. So basically, this means that the edges are metallic, and you could have sort of electrons to be transported along the edges only. So we thought zigzag edges, armature edges don't work in the same way, but zigzag edges are very interesting. So we had some clue that this could be the reason. And of course, one of the ways to really understand the edges is by unzipping boron nitride tubes. This is something that we have done recently. So we can unzip the boron nitride tubes, and we have this open, these tubes open along the axis, and we're now trying to understand the edges of these things. Because there are some other calculations that you passivate the edges with oxygen or sulfur, and this is were done led by Umberto, who happened to be my brother. So then you have basically metallic states here on the edges. So the edges are very important in these materials, and that's something that we need to understand and control. Let me just move quickly to tungsten disulfide and the clusters and monolayers. And this is something we're doing within this MURI team collaboration, and also within the MERSIC collaboration. This will be the cover of Nanoletters. And so you have this sandwich structure that I talked about. You have the metal, you have the sulfur, selenium atoms there. And the important thing here is that the band structure changes when you go to a single layer. So just like graphene, when you go to a single layer, the electronic properties change. And here you have the infinite crystal. You have, this is the valence and conduction, but you have an indirect band gap, which is this one. And for a single layer infinite crystal, you have a direct band gap. So basically, the indirect becomes a direct band gap. And there's work by Kim-Fan Mack and Tony Hines back at Columbia. So in 2010, they found those by exfoliating molybdenum disulfide. It was not tungsten disulfide. Those a single layer, you could see a huge photoluminescence just from a single layer, and you have the PL, this signal. And the explanation was that, again, that you have, when you go to one single layer, you have the direct band gap. When you go to two layers, for instance, this is a two-layer part, there is no PL emission. Though there's a little bit more. So the single layer is very strong. This is 2 layers, 3 layers, and you can see that it emits here. So that was something. So the question would be, what happens if we're trying to make tungsten disulfide, because many people are working on molybdenum disulfide. We said, well, let's try a different system. So back like 10 years ago, we did some work on the tungsten disulfide nanotubes. By using tungsten oxide nanorods, we passed through H2S, and then we're getting tungsten disulfide tubes. So this is something we did long time ago. But also we did with Umberto and Gotthard Seifert some calculations of the tube. So what happens when you roll a tube in different ways? And we found a similar thing. So all the zigzag tubes have only direct band gap, as you can see it here. And the armature tubes, they have a lower, but they still have the indirect band gap. So it was very interesting that all zigzag tubes, if you manage to make all zigzag tubes on molybdenum disulfide or tungsten disulfide, you also have a direct band gap. Of course, it's easier to work in a flat system, but here, so basically calculations, so the zigzag tubes, they only have direct band gap, the armature tubes have the indirect and direct band gap. But they were lower than the bulk, depending on the diameter. These were very strained tubes. but still it's interesting to show that there's some work on this. So using the knowledge we had from previous, so we basically decided to use the metal oxide and then pass to H2S or sulfur, and we ended up having these triangles. So when you look at these triangles, then you get, these are monolayers. These darker spots start to grow the double layers. And we did some Raman, and we did some other characterization. We found that the edges of these triangles were zigzag, so which is interesting. And according to calculation, the zigzag edges are also metallic in the systems. And of course, you can compare the Raman peaks. Here in these systems, you have two main modes, which is the E2G, which is an in-plane sort of mode, which is, these are the sulfur atoms and the metal atoms are going in this direction. And you have the A1G, which is like a spring-like mode. Then we noted that it was very interesting. From this sort of triangle, we saw an enhanced luminescence from the edges. So it was very, very enhanced. We could see PL here from the center, just like Mack and Tony Hines found. But here the edges were very, very special. We had like 35 or more than 40 times the intensity here. For instance, P5, which is this edge. And these are the Raman signals. The E2G and A1Gs, they are behind here. So it was very, very nice, and that's why you have this very nice image of the edges. You have this luminescence they emit. So you can scratch it, and then we thought, okay, if you scratch it, maybe you have those exposed edges, but it doesn't work that way. So when you scratch it and you expose it to air, the luminescence is not there. So it's something within the process that we believe is a chemical passivation, which has to deal with the sulfur content. Of course, this is the way you could have zigzag edges, but you could have also armchair edges here, or you could have terminations with sulfur, terminations with metal. So there are different possibilities, and we're trying now to understand these edges and what is the origin of this luminescence. Along that direction, so with Ice and Humberto Gutierrez, so it was by luck that we found resonance of these monolayers. So you have these two peaks, and when you use the 488 nanometer wavelength, you have the LA mode, you have the 2LA mode here, you have and you have the E2G, these two modes. But when you use the 514 laser line, you see that the 2LA mode becomes resonant, and basically you see the intensity increases a lot. And that only happens with monolayers. So that was an indication that you can really identify single monolayers from bilayers or trilayers. And here's, you can see the resonance here. So as you increase the number of layers, when you are using the 514 line, the intensity comes up all the way here. So that's an indication that you can really use this technique. At least tungsten disulfide, it should work for other chalcogenides, but you have to use other laser lines. But the tungsten disulfide with 514, that's the one that is resonant. And here you can get that mappings of the 2LA mode, which is the resonant mode. So it is very intense when you have a single layer. These areas is where you have a single layer. So this is the single layer. When you have 2 layers or 3 layers, basically there's this resonance is killed. And I think that's a very nice outcome. So you could use fluorescent microscopy to identify monolayers, and this is the way you can see there's monolayers, and you have this double layer, then there's no luminescence there. So I think these are the ways that we should, quick ways to identify monolayers would be fluorescent microscopy. We're now doing some low temperature PL measurements, and this is just some data that Isaac got recently. And we just saw that how the peaks changed, and it's around 18K, and this is how the peak position changes. There are some shifts, and also in the full width half maximum, there are some shifts, there are some transitions around here. So we're now trying to analyze and understand this data, but I think there are lots of things that are happening with these layer structures. So the other things we're working on, this also in collaboration with Bing Crespi, we noted that depending on how you grow your systems, you can get different shapes. So you can get these butterflies, which is you have a grain here, a grain boundary here. You can get stars, David stars, you can have triangles. and you can have hexagons. So you can basically go to the same location using different microscopy techniques. You can use AFM, you can use optical microscope, you can use SEM, and of course you can see this 2LA mode, which is very intense. That means that all of these are single layer. So we have some control on that. This is David Starr, these are the things. And these are, of course, these are other structures, hexagonal islands that we're looking into. So with hexagonal angles, you can have alternating zigzag edges, for instance, but you have passivation differently here. So we have metals here, we have sulfur there, and some of the calculations by Bing Crespi. So depending on the sulfur chemical potential, so you could change, if you have an excess of sulfur, then you end up having these triangular islands, but you have not much sulfur, then you start to get these different morphologies. And I think it sort of works. So I think this is a nice thing. So we can control the shape and the morphology as well. And the luminescence changes by having different shapes. So you have very sort of roundish shape. You have this luminescence coming from these very flat edges here. And in this case, when the edges are very flat as well, you have all these in these cases. So we're trying to understand what's happening there, why we have luminescence in all the cases, on all the edges there. And of course, we have to correlate that with TM or STM. And these are different. You have armchair edges and zigzag edges, and these are the different configurations that you can have. So I think related to the synthesis of these materials, one of the points would be, can we make extended sheets? Not only the triangular islands, can we grow extended sheets? And this is some work that Anna, Laura, and Nestor have done. So they have managed to develop a technique to grow extended sheets that could be transferred to substrates, and then you can do lots of measurements from there. So the idea is using a similar system, but you use this system under vacuum. And of course, you have to play around with different things, but you can tune the system. The port-to-port is a low-pressure CVD, and once you get that, you can get the monolayers, you can transfer them on PMMA, then you have to use HF, hydrofluoric acid, which is not nice, but it works. And then you can transfer this like centimeter by centimeters in white. And of course, we know that this is single layers because we have this 2LA mode. And with the different lines, so we have 488 and 514. And these are the images, high resolution images of single layer, monolayer, 2 layers, and 3 layers. And so this is the way they look like. So sometimes you have these sort of defects there. And these are recent images that we got from Oak Ridge National Lab from David Cullen. So we have here grain boundaries that we're trying to analyze. And this is the way the material, sometimes the material looks like. So you have single layers here, you have double layers and triple layers here. And so you have some vacancies there. So it's very interesting that you can observe this dynamically in the microscope. And you can see that in some cases, because you have one sulfur on top of the other, you can have, there's no sulfur there, but here there's one sulfur that was ejected from the system, and you still have one sulfur there, and there's one sulfur that is ejected from the system. So trying to understand defects at this level is very important. How do you start ejecting sulfur atoms, and what the properties, how the properties change? So you have these vacancies, or you can passivate these vacancies with something, and then we get different properties or even enhanced luminescence that we're looking at. So this is the materials that we're making. I just go through in collaboration with Jun Shu and Tom Maluk. So basically, he grows the crystals. Tom grows the crystals from chemical vapor transport just by exfoliating this tungsten disulfide. They also found just by exfoliating the tungsten disulfide, you find also this luminescence, this very sharp luminescence PL peak. And we find the 2LA mode, so which only happens for a single layer. So we confirm that our CVD and this exfoliated one, it sort of works in the same direction. Let me just show you some of the applications because there's some applications behind, and there's some history about applications, and it's just to show you how science works. So imagine in the 18th century, imagine Michael Faraday giving a lecture about electromagnetism. So that happens at the Royal Institution every week still, every Friday night. So there's a public lecture. So people from the public come and listen to Michael Faraday. So that's the 19th century. So, and the secretary of the Chequer in the UK, Mr. Gladstone, asked Faraday after his talk, Mr. Faraday, do you really believe that electricity could have a practical use? So Faraday answers, Mr. Gladstone, I'm convinced that one day you could tax it. So that's the way we have to convince our politicians that when we're doing nanomaterials and we're doing all these exciting discoveries, this is some way to attract. So you can have more taxes, then they can raise their salary and they can do lots of things. Okay, so this is related to some applications. And this was done together with Nestor, Perea, and Anna. Of course, they saw what happens when you with the photocurrents with the measurements. So in this case, we decided to grow a bit thicker. We can control the number of layers, so we grow like 10 layers of this tungsten disulfide. So for instance, when you use the 514 line, when you have several layers, there's no enhancement in the 2LA mode, so there's only the 2G. Why we decided to use this sort of 10 layers? Because we tried with single layers, and we're using the CVD grown tungsten disulfide, and the contacts is always very resistive, and there was not much you could get. So we had to use few layers, and this is some work that was published just recently, and they can see the magic number of layers around 10 layers. So when you have 10 layers, the mobility also increases, but after 10 layers, it also goes down again. So we decided, okay, let's try 10 layers. So we did the circuit, that's the device, and we started shining different lasers. So you can see the on-off when you shine different laser lines, and you can see as you increase the energy, then basically the responsivity increases as well. And this is the photocurrent as well, which is very high. So actually, one of the important things is that you can use very high currents and the device still works. So this is some previous work with molybdenum disulfide that was published, and this is in our case, so this is the way it responds. But I think you can see this time, it's around 5.3 milliseconds, which is much better than the response time is much better than any of the other ones reported. So it's like, in this case, it was 50 milliseconds, we have 5.3 milliseconds. And of course, it could be controlled. Now we're trying to do a study which is more detailed depending on the number of layers, but tungsten disulfide appears to work nice. This is our work related. I have 1 minute. This is our work, so you can see termination. And just to finish, so this is just to leave some thoughts here. These are calculations performed by Umberto, and then basically what he found is that when you can play around with tungsten disulfide, molybdenum disulfide, tungsten diselenide, molybdenum diselenide, but it's important to use tungsten diselenide and tungsten disulfide, for instance. Because here you have the single crystal, you have the crystal, which is the indirect gap, the single layer, you have the direct gap, band gap, this is the tungsten disulfide. And when you have a bilayer system, you start to have this indirect band gap again. But if you have a bilayer system, tungsten diselenide and tungsten disulfide, you can reduce the band gap by almost 1 electron volt, and it's still direct band gap. So having these systems, you can basically tune, you can do a band gap engineering just by sandwiching different materials. So this is just some possibilities with the sulfides and diselenides, but there are other possibilities when you try other materials. And this is something that is just starting. I think this is something that is exciting. And related to this, we have just managed to grow this tungsten disulfide on top of tungsten diselenide, tungsten disulfide on top of molybdenum disulfide, and this is some preliminary work that we are doing. And I just finished with some joint work with Josh Robinson on the growth of these different layers. And I think I just want to finish and say there are lots of challenges ahead, and that's why these 2D layer materials are very important. And I just finished with, I have to thank my sponsors so that they are happy. And so if you have questions, of course, we're here. And so we have this newly created center that is part of the MRI and and the different colleges. Thank you very much.